Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week. And today's topic is temperature, heat, and scales. Okay, not the kind of scales that you get on to weigh yourself, but temperature scales. And this actually turned out to be way more fun for me to produce than I thought it was going to be. I thought it was going to be a little bit on the mundane side, but actually this was sort of fun. So hope you enjoyed as much as I did putting it together. So let me shrink myself here and let's get started. And of course, as always, we need to start off with some definitions so that we know exactly what we're talking about here. So the definition of temperature is the average amount of kinetic energy, or movement if you will, of the molecules that make up a substance or object. Now it's important to point out here that this is the average amount of kinetic energy, okay? Each individual molecule can have different motions, different vibrations, all sorts of different behaviors, but this is the average amount on a given object of all those molecules, how much motion they actually have. Now, heat is the total amount of energy of those molecules that make up an object or a substance. And it's actually possible that object one, let's say we have two objects, object one may have a cooler temperature than object two, but object one can actually have more heat because it occupies a greater volume, okay? Before I get to that last point. So here is a sort of a crazy example. Let's say that a cup of coffee, okay, hot off the press, has a hotter temperature than the Atlantic Ocean. Okay, maybe the coffee has a temperature of 100 degrees Fahrenheit and the Atlantic Ocean has a temperature of 75. Okay, but the Atlantic Ocean has way more heat because it occupies a much, much larger volume than that individual cup of coffee. So that's how you take a look at the difference between temperature and heat and how they actually compare. Now, if all molecular motion were to cease, in other words, molecules were not moving at all, then the temperature is said to reach absolute zero on the Kelvin scale. And we'll talk more about these different scales in just a second. But again, this is a theoretical value because obviously we have never observed zero molecular motion. If we did, we wouldn't actually be here to observe it. All right, so there are three temperature scales. The Kelvin scale is the one that is used by the scientific community. Every time I download model data, all of those temperatures are in degrees Kelvin. So if I want them to display in Celsius or Fahrenheit, then I have to do that conversion in my script to get it to come out that way. So the Kelvin scale is the one used by the scientific community, and it was invented in 1848 by British physicist William Thomson, who was also known as Lord Kelvin, hence the name, the Kelvin scale. Now, the centigrade, or the Celsius scale, was invented in 1742 by the Swedish astronomer Anders Celsius. And interestingly enough, and I did not know this, initially the boiling point was set at 0 and the freezing point was set at 100, but then was later reversed, and of course it makes way more sense to have it the way that it is now. And then finally, the Fahrenheit scale was invented by German-born Dutch physicist Daniel Gabriel Fahrenheit. He invented the mercury thermometer back in 1714, and then later the Fahrenheit scale in 1724. So these dates actually go backward. The mercury thermometer was invented first, the Fahrenheit scale 10 years after that. Then in 1742, 18 years after that, the centigrade scale was invented, and then it was more than 100 years after that before the Kelvin scale came along. So here we have three thermometers, and we're going to assign Kelvin to one, Celsius to the other, and Fahrenheit to the third. So for absolute zero, where there is no molecular motion on the Kelvin scale, that is equal to 273.15 degrees Celsius below zero, okay? Or on the Fahrenheit scale, minus 459.67 degrees, okay? Now, if we get to the freezing point on the Kelvin scale, it's 273.15, and on the Celsius scale, it's 0, and on the Fahrenheit scale, as you all know, it's 32. Now, notice that the magnitude of a Kelvin degree is exactly the same as the magnitude of a Celsius degree, okay? Like from absolute zero to the freezing point, they both change by exactly 273.15. But the Fahrenheit scale is doing something very, very different, and we'll talk about that in just a second. And then finally, the boiling point for Kelvin is 373.15 degrees Kelvin. Celsius, it's 100 degrees Celsius, and for Fahrenheit, it is 212 degrees Fahrenheit. So here are the conversion equations, in case you're interested, to get from one to the other. Now, going from Kelvin to Celsius or Celsius to Kelvin, it's actually quite simple. From Kelvin to Celsius, you simply subtract 273.15 degrees, and if you're going the other way, you add 273.15 degrees. So that's pretty basic. But to go from Celsius to Fahrenheit, it gets a little bit more complicated. You multiply the Celsius value by 1.8, or if you prefer a fraction form of that, 9/5, and then you add 32 to that. If you're going the other way, you subtract 32 first from the Fahrenheit reading and then multiply that number by 5/9, which is the reciprocal of 9/5 or 1.8, okay? So here's an example. You're starting off with 5 degrees Celsius. You multiply that by 1.8 and you get 9, okay? And then you add 32 and you get 41 degrees Fahrenheit. So 5 degrees Celsius is 41 degrees Fahrenheit. And if you're going the other way, 50 degrees Fahrenheit, you subtract 32 and get 18. You multiply that by 5/9 and you get 10. So 50 degrees Fahrenheit is equal to 10 degrees Celsius. And I know I've mentioned this before, but many, many years ago, and I don't know what inspired my brain to do this, but I came up, for me anyways, with what was a simple way to do these conversions on the fly, or at least get them within 1 degree, okay? So if I know that 0 Celsius is 32 Fahrenheit, I know that for a fact, and that's sort of easy to remember, then for every 5 that the Celsius goes up, the Fahrenheit is going to go up 9, okay? So if we start off at 0 and 32, if 0 goes to 5, then 32 is going to go to 41, because we're adding 9 on here and 5 on here. Now let's do it again. If we go from 5 to 10, and the 41 is going to go up 9, then it's up to 50. One more time. 10 up 5 to 15, and let's see, where were we? 10 was 50, so we go up 9, and so it's 59. So 15 is 59, and so forth. 2068, 2577, 3086, 3595. Same way the other way down. Minus 5 would be 23. Minus 10 would be 14. Minus 15 would be 5. And minus 20 would be minus 4, okay? So you have to go down to about minus 18 degrees C before the Fahrenheit numbers actually start to become negative, okay? Finally, here is a graph of the Celsius and the Fahrenheit temperatures going from absolute 0 up to the boiling point, okay? So if we label this here, you've got minus 459.67. The green line is Fahrenheit, and the orange or tan line is Celsius. So you've got minus 273.15 Celsius, minus 459.67 Fahrenheit, and then for the boiling point, you have 212 Fahrenheit, or 100 degrees Celsius. But look what happens in between. They cross at minus 40 degrees. So if the temperature is minus 40, it doesn't matter whether or not it's Fahrenheit or Celsius, because they're both exactly the same at that specific temperature. And what's really interesting, I thought, is that if you look at the range from absolute 0 to the boiling point, Celsius, it is a range of 373.15 degrees, but on the Fahrenheit scale, it is a range of 671.67 degrees. And guess what happens if you divide 671.67 by 373.15? You get 1.8. And that number, of course, was in the conversion formula going from Celsius to Fahrenheit. So it all works out mathematically, okay? Now, the reason that the Celsius scale, that the people that adhere to that thought it was so convenient, is that freezing was 0 and boiling was 100. Okay, so it made it very, very easy to tell the difference between the two, whereas with Fahrenheit, 32 and 212 aren't exactly easy to remember numbers. They are if you're an American because you grew up with that, okay? But in terms of just, nice even round numbers, they don't really work out all that terribly well. But I've heard the argument that if we went completely metric, then all of those recipes that have a dash of this, we don't know what the metric equivalent is for a dash, and so we need to keep the recipes simple and keep them in an American form. So that's the counter argument to switching to metric. All right, that is an exhaustive talk about 3 different temperature scales and also heat and temperature. I hope you found that at least somewhat intriguing. That is bonus weather video number 3 for this week. Number 1 for next week will be coming up on Monday, and the next daily update will be coming up on Monday as well. Hey, enjoy the beautiful weather on Saturday, the just slightly less than ideal weather on Sunday, and by the time I talk to you on Monday, it's probably going to be raining. You all take care, folks, and we'll talk to you soon. See you later.